Welcome to the Rawpter 9 assembly and crash recovery video. This is for folks that are looking to build the Rawpter 9 that may have found it on the instructables. So the Rawpter 9, it's a drone. It represents our greatest achievement so far in our maker world between Connor and myself. It's a 4-layer board. And then of course all that it takes to mount it and get it into the air. But a 4-layer board based on the ESP32. It's got a GPS. It's got an IMU, as you see there in the center. It has a barometer to give you altitude. And it has a magnetometer or a mag to give you your compass. So it looks pretty awesome. And it can pretty much have autonomous flight. And here we are testing it through our field. We call it Hacksaw Hill, affectionately named after a prop about cut my pinky off. And here you see it. This is our bigger frame, bigger propellers. I think they're 10-inch. That has the Rawpter engine on it, and Rawpter flight controller. You notice there's a couple little pool floaties under it. This is us flying it with what we call training wheels. That way it can drop without any issues there, without any breaking anything. Now, we've flown it around a lot, and in the early days it was terrible. We'd break props every time we went out. It was very expensive at that time, and what the Rawpter has evolved to is now really a crash test flight controller. It's designed where the components that are the crumble zone can be readily mended, which I'll show you in this video, and you feel free to skip ahead based on the chapter index to anything you're interested in, because I'm going to ramble here for a while. There it is, taking off really awesome. Yeah, we made it where it's very friendly for crashing. It has a center metal roll cage. Basically, it's actually made of metal. It's like a thin sheet metal over some type of fiber board that we just bought that. You could 3D print it and then take aluminum and sheath over it as well. But it's important to have that metal interior. That way everything else can fold and crumble in a very bad impact. And you're probably thinking, why in the world would you make a drone that would have a bad impact? Well, that's what this Rawpter is all about. It's about having code that you can change every line of code on yourself, so that you can then code in acrobatics and autonomy and different things and push the limits of flight, which may then result in a lot of crashes, of course, right? As you're pushing limits, you're going to crash. Now here we are doing some landings. Like, that's a really good manual landing there.
That's for sure.
Usually that's Connor doing that over me. There's one that's a little harder. And this is the kind of stuff you just wouldn't want to do with a $1,000 DJI drone, because you just lose your $1,000 bucks. There we go, a little harder landing there. I think this one goes end over end. Yeah, that one's end over end. But it's pretty robust for those kind of landings. It really is. Where things really go bad is when you write a routine for autonomy and it gets away from you. Like, you may have thought that your yaw had the wrong sign on it, so rather than getting closer to a GPS location, the error grew and it flew away from it and sped up, went super fast, and then just dove into the dirt. And when that happens, you're hitting at 30 miles an hour, so that's what you get right here. And actually, I look at that and think it looks beautiful. This one too, this is another one. It's beautiful. And I'll show you why that's beautiful, even though it's hard to recognize the drone right here. Let's look at it here on the bench. That'll give you a better idea of what really happened there by design. So here it is sitting upright and spread out, that same image of the crash, one of those crashes there. But what you notice is the metal roll cage protected the battery, and there was another roll cage that's pulled off that is 3D printed that protected the flight controller you see there on top. But look at where the arms broke. That's really what you want when it's a catastrophic crash, like a 30 mile an hour into the dirt kind of crash where it's tumbling end over end. You want the battery to be protected. You want the flight controller protected. And so basically it's like a roll cage design with an outer crumble zone, and that crumble zone is the arms. And so here you see what's called the exploded view animation coming out of Autodesk, and you're getting all the pieces being disassembled. So it's pretty neat. You see the arms, those are 3D printed. That top grill there, that's like the top roll cage, just a cap to protect the flight controller. That's 3D printed. Then you have your ESCs there, and you see the motors. The propellers, we go with the foldable kind because I was just going broke having just rigid propellers on that. You really want to get the design and everything working perfectly before you switch out to rigid propellers. And I personally don't even see a need for it. Even DJI, our $1,200 bought DJI, has foldable propellers. And so they take crash over crash over crash over crash, and they're only like $5 a bag. So they're real good. But the 3D printed parts, what we're going to look at here is how you make those arms, and we'll look at how you put metal inserts into the arms. And then at the end here, in several minutes down the road, you can fast forward to it or scrub for it. I show how you don't even have to take it apart to fix the damage that you just saw there on that bench. I actually just use a soldering iron, and since the 3D filament is a thermoplastic, you can just bring it back together. You do plastic welding very much like TIG welding without the gas there. But the easiest way is just 3D print again. So here you see one being born. And so let's take a look at here after this crash. I show you how quickly you can get back in business there for free, basically, or the cost of filament. And like I said, you can scrub forward 10 minutes or so, and you can see how I actually, for entirely free, I just use a soldering iron to heal these back together. I just do some like groove welds, plastic welding to melt the plastic and then fuse it back together. That's pretty neat. So these are attached. There's M3 screws. They're only about 3 or 4 millimeters long, and they thread into inserts. So right now I'm taking apart that. I'm taking the Allen wrenches back out of there, or with an Allen wrench, I mean. And feel free to scrub along through here. I'm just going to talk through it. Don't want to miss anything. Those who are new, I was very intimidated, of course, years ago, but when I first started soldering and things, I'd get a lot of anxiety before I'd do a big project, and all that's gone now, of course, after so many projects over the last 10, 15, 20 years. But I know someone coming new, that's the beauty of YouTube and instructables is you can see second by second what the person is going through and what challenges they have in that. Now you can tell one thing I want to get is, even though I'm pretty good with the thumb there, I want to get me a little portable screwdriver, and so I can just chuck in an Allen bit and make short work of this part here. My bench I'm working on, it's just a little folding table off to the left. It's nothing elaborate. I'm not out in the garage or anything. I just got a table upstairs, and we call it the nerd room or computer room. A lot of times it's the nerd room. But what you got in there is everything, everything for making, including my wife's crafts and things. So there we go. I got the top screws there. And now we're going to flip the rig over. The battery is definitely disconnected now. We wouldn't want any false starts to occur. And then there's 2 screws on the bottom. But this very bottom is actually where the battery's held on this design, the way I have it all assembled. And so I'll stick the Allen wrench down in between the 2. And you may have to scrub back to the main picture to see how it is. And so one of these was a little sideways, so I had to get at it from the side. But actually, normally I just go through the holes there with the Allen wrench, make sure I have an Allen wrench long enough to reach. But that one was a little crooked in there. It must have, the insert was crooked in the plastic. We'll see that in a second. You see some dirt there on the right side by my right hand. That's dirt from the field where it bit the dirt, literally. There we go. So now we got one of the ends out, and you see the four little inserts in there, little metal inserts I just pointed at, and there's two more on the other side as well. Now those inserts, they're not overly expensive, but at the same time, there's no sense in throwing them away. They could be reused really forever. What you get into is sometimes you'll have melted plastic get in on the threads, and then it's real hard to get your M3 bolt into it. So what I do, as I'll show you here shortly, is I'll remove them with the soldering iron, and then I'll just take a lighter and I'll burn them off. Just like when I worked for DuPont years ago, they were the ones that invented nylon back, 80 years ago or more. And nylon, when you make that process, the bummer is the piping, that as it's slug pumping through the pipes, it'll eventually put a skin, basically like a skin of plastic, on the pipes. And so they have this melt process they do, which is essentially you putting it in an oven and getting it out of there. And so I do that with a cigarette lighter. There you go. So there's another 4 coming from this arm, and then there's 2 more on the other side right there. And now I gotta fight these other ones. There we go. That one got right on in there. Right on through, just barely long enough to make it on through, and then loosen those up. And actually these arms, I designed it where you could go with one through bolt and then have a nylock nut on the other end. And I haven't explored that yet, but they're actually designed that way. It's hollow on the inside of the arm where you could throw that, all the way through. And then that allows it to clamp top and bottom of that arm versus just have the inserts being grabbed. And I actually like that much better. I think that's a better design. I just, at this point, hadn't ran it through them. But the arms definitely can do that if you get I believe it's like a 50 millimeter length. Okay, so now we're going to get those inserts out of there. We're going to reclaim those so we're not buying new stuff. This thing's designed to be crash tested over and over and over. We definitely don't want to break the bank because we're replacing components that really don't need to be consumable. So right now the iron's heating up. And what I do, I don't use the same tip for this as I would for soldering. I do use the same stick. I use the same Weller soldering iron, but I use a different tip when I'm doing this. And so I just turn it up to around 300 Celsius and stick it in there, and the plastic melts. It's not frying, it's not burning. I'm just slightly exceeding the melt temperature of the filament there. So whatever your filament is, just add like 50 degrees on top of it to make short work of it. You see them popping right out of there. And you can see there's plastic still on the other ones. It's not that big of a deal as long as it's not in the threads where the bolt engages. You could just let it melt on the iron when you install the new ones. I'll show you that here in a minute. All right, and there's our other one. I don't know why it feels therapeutic to watch this. It's therapeutic to do it too. A lot of times I'll just play the news or something like that in the background because there's always something crazy happening in the world, and you hear all that while you're just chomping through all this. There we go, and that's to be chucked. No need to hang on to this piece now that I took out the inserts already out of it. But like I said earlier, I'll show you how actually I could have just skipped taking it all apart and just welded it all back together with that iron, and we'll do that. And usually I'll do the weld trick first, and I'll do a few times where it'll break and break and break, and after a while it just, I don't know, it just feels like it's a good time to start new and get it looking good again, because each time you weld it, it just looks a little more like Frankenstein. So here is where I'm doing the melt process, or basically I'm just turning it to carbon. I'm burning that stuff all the way down. It does not set off my smoke detector. You don't want to breathe those fumes, though. You don't want to do that. So kind of keep the ventilation away there. If you're new to soldering, they actually sell these little devices you just set on the table that'll grab fumes, run them through a filter, and then it'll just exhaust it into the room. They're not very big or anything, but it just keeps that out of your face. And then any carbon, it'll catch into the filter. And like I said, this part really, you could get away with not doing it. If you look at the threads down the hole and you didn't get any plastic down into the hole that's hard, you really don't even got to do this. Now, one thing, I believe these are brass fittings or whatever they're made out of, they actually did soften. They'll soften themselves too. So if I put a death grip with my tweezers there on it, as it heats up, it'd start deforming. And so you don't want to do that. So you want to grab it in a way that you're not going to deform it as it heats up to burn off the stuff. Another way you could do this, if you had like a crucible or something like that, and a little propane torch or MAP gas torch, that you could just get them all at once out in the garage, just nuke them all at once. That's a good way to do it. Is pull them out, throw them in a bin, then whenever you finally run out of your good ones in your good bin, just go out and torch these things. And if you're one just to want a camera drone, you'll probably never have to do this. It's the reason this video is being made is for those who like to push the limits of flight and their code, where you're coding in some acrobatics, where like you flip a toggle switch and you make it barrel roll 6 times, that kind of stuff. And as you're dialing that in, unfortunately, it results in a lot of hard hits out in the field. And there you go. So this is the big one here. It's a very number one basic thing, installing an insert into the plastic. Now, if you've never seen this before, it is a great way to join things. You print things to be assembled rather than just having them click together or taking your bolts straight into the plastic. This just is way cooler. You're going in the metal and you're going in hot, and it's forming an interface fit very snug into the plastic. And you notice when I do this, I actually don't go all the way in. I leave it out like at least 1 millimeter, and then I use the flatness of my ceramic tile there to make sure it's flush sitting against the part, because I want that part to draw up everywhere. I don't want it sticking out
I also don't want it such that when I tighten it up, it will want to pull the insert back out. So I want it perfectly flat. And the way to do that is leave a little bit, like a millimeter, still above the plastic, and while it's still hot, quickly push it down flat, and then you'll have that perfectly flush installed insert. And these are tips learned the hard way. You know, I had some where I sunk them too deep, and then when you get to tightening them up, the next thing you know, you're spinning it in place because you just over torqued it or something. And if you get it just right like this, then you can torque them up really good, really snug, and you don't pull it back out of the plastic. It's not rocking on the insert or anything. So there's that one. And now this is a different material. The other material you saw there was likely the PET-G, Rapid PET-G. I'm using Elegoo, I believe that's how you say it, Elegoo 3D printer, and I had that Rapid PET-G. This here is a nylon infused with carbon fiber. It melts much higher. It's like this one melts at 280, where the other one was like 250. This one I actually didn't print with structure. I wanted to see how well it would do. And really, the PET-G you can print without structure, and it pulls it off pretty good, straight out of the box, even though it has these steep overhangs, as you see there. But this one prints so like inviscous. It like runs out of the nozzle. It is remarkable how they got the settings dialed in on Elegoo in their config for this material, because it is always running like when it stops. And that's where you can tell without structure on it, those bridges just sag right off the whip. But I wanted to see how it would do, and it showed me. It's ugly, but it's still strong. It's very strong, very super light and very strong. What I found with this material is that definitely it's light, but PET-G will flex. Like when you grab it on the ends and bow it, you can feel a little bit of flex, and that flex will affect flight. It will like change the dynamics of turning and things like that. Not anything you could ever tell, but there's no doubt that when it flexes like that, it's changing the axis and creating an inward bow on the propellers and things like that. Where these, it does not feel like that. It is just rock solid and so light. And I also found that the break point on these is different. Now, I haven't crashed too many since I had that, or when I do crash, they just never break. But this one did not break in the same location as all PET-G have always broke for me. They break in that skinny side, either close to the back or close to the motor, one or the other. It's in the skinny part of it. This material here actually broke in the part that's sandwiched between the two frame plates. It broke in there, which shocked me majorly, because you have all that reinforcement there on the back side that I put. But yeah, it just chopped it right down through. Now, and so that's another reason I would want to just run one long 50 millimeter bolt through it and sandwich it in there. Now, the bummer though is anytime like you keep making something less and less prone to break, you're really just transferring those forces onward into something else. So if I get this where it is just bulletproof and won't break with a 20-mile-an-hour crash, I may find I cracked my frame. And then I don't want to do that, because making those frame plates out of metal or buying them just isn't cool. I'd much rather have an occasional, one of these here. You just set it up to print out overnight, and you get all four of them. You always have a spare laying around, and you could do the metal, the plastic welding trick that I'll show you after this, and and you're flying again very quickly. But you go cracking your frame, now you could cause damage to your battery, and that's just not cool. So that'll be my limit. After I get it to a point where, hey, yeah, nothing's breaking, I definitely won't be looking to beef up anything else, because you have to design in a crumble zone. And that's what they realized in automobiles, years ago. The days of the giant, station wagons, of those really solid frames that would just, no one would survive in a crash after those. Where in modern cars, they can really absorb energy up under that hood area because of a crumble zone. So that's where these arms, that's what we're wanting to be the crumble zone. And I've even thought, like on a bigger drone design, on putting in some type of breakaway design where when it lands, it'll just allow it to fold like the propellers do, because those propellers, they just never break. And I'm sure I'll break them someday. But with them being foldable, when they hit, they would have to hit just right to snap. They just fold in, and not a problem. I've hit gutters and things with them, and it survived it. But man, straight props, they break. You just lean over 15 degrees on a takeoff. Next thing you know, you got broken props. So again, the idea is make this sucker where it can roll around like a softball on most casual crashes. Yeah, that's a really neat material. This material flows so well, this carbon fiber infused nylon, that you can't see the layers when you look at it. To look at it, it looks like one of those sand casted materials. And the reason is because it's just coming out of there like ketchup. I mean, but I guess faster though. It is very much just flowing out of there. And so, and the particles of the carbon fiber and all, it just creates this randomness where it's almost like this grainy side, rather than seeing the layers that you would normally see in PLA and ABS and different things. And I have used PLA as well, just very inexpensive PLA stuff you can get right there at the Hobby Lobby. Of course, you can always get stuff online, Amazon, very affordable. Rapid PET G is a higher melt point, and I believe a superior to PLA, and it's very cheap. You can get that for $14, $13 on Amazon. And PLA is one of the most affordable out there. It's more environmentally friendly. And that blue arm that you saw in the beginning of this, like right here, I think it might show up. Yeah, that blue arm right there. It's kind of funny. That technically is the weakest arm of the bunch, but that sucker has lived longer than many, many. Now, it used to have 3 siblings that long are broken, gone, but it is PLA. That blue was printed PLA, and the black here is either some are PLA, maybe a couple or maybe one, and then the rest are PET G. And they all broke in the exact same spot under that same crash. And now I'm putting the arm on, and so you most likely could picture how this works, just like it did before. You just slot it in there, and I put the cables to the ESC underneath, like kind of where it's like straddling the lower legs of that arm are straddling the cables coming under there, so it just kind of corrals the cables all on its own. And you see the name Rawpter 9. Well, that's because it's the 9th iteration of this design. Now, not every one of them went to fab. Some of them, like I jumped 2 levels, because once it went to a 4-layer board, that's when Autodesk Fusion 360 no longer let me edit it when my professional license ended. That I had a professional license I used. from my work. And when that ended, I suddenly couldn't do anything else with the file, you know. And I knew I couldn't share it because it was a 4-layer and things, so I switched over to KiCad. And then what was awful, I had a version of the board where I used a different ESP32 module that had its own built-in antenna. And I did it again, something I did 10 years ago. I learned this lesson 10 years ago, that you don't put your antenna directly over the ground plane. And for some reason, I stuck that ESP module right in the center or near the center there by the IMU, and it just totally killed the antenna capability. So I couldn't do Wi-Fi with it at all. That one went all the way to fab. That one went all the way to built. And then I had my aha moment that, oh man, I done made this thing where the Wi-Fi doesn't work on it. And that's where now I go with that it's like a room, I don't know how you say it, module, where it has these Castle connectors, soldering pads that really make it easier for soldering by hand. The other type that the pads are underneath the module was tough. That design was tough, Rawpter 8. This one's much more friendly for you guys just doing it with a soldering iron or a hot air station. And then you see where there's an antenna coming off of that one, that silver square in there. There's a little antenna coming off of that. I decided to get the antenna totally separate from the board. There's just a lot going on those sensors that you don't want to mess up anything due to any cross communication kind of EMF issues and things like that. So I just went ahead and got it off the board. However, it is designed where you could use the other module and it'll just have an overhang. It'll overhang about a 1/2 inch with the antenna overhanging out there. So you could use the other type module that has a built-in antenna. It'd work fine. So you see it just snugging up. Look how snug that one got. I mean, this is the chiz. You know, a lot of years I used to think it was cool to make things snap together and different things, but man, when you're trying to get, you know, something that weighs a couple pounds flying around, holding a big heavy battery in midair and doing these very hard turns on a dime up in the sky, yeah, you don't want that thing coming apart. You don't want to just go bolt to plastic on that. Not at all. I've had some things happen. Like I'd have a crash and didn't realize I had a crack. And then I was up midair and I take a hard turn and then that thing lets go midair. It looks like a TIE fighter getting shot right in space there. It just comes disintegrating and falling back to the earth. It's fun. It's funny, but it's fun. And there I am just kind of showing it how it flexes. And there's definitely a difference between those two. So now let's look at this. Is a different approach. This is the quick approach. This is the approach where you want to get right back out there. You run inside, you get you a Coke, and you get the arms back on. So no disassembly of anything. So the first thing is, if you're like me and you crash 30 miles an hour into the dirt, first thing is you got to get the dirt out of the wound. Like in this one, it wrecked so bad, dirt got into the fracture point. So I'm just hitting it with isopropyl alcohol, and I'm going to try to get that dirt out of there as best I can. I mean, we're not doing pressure code welding on vessels in industry here, but it'll definitely do better for you if you get the dirt out. Get the grass out of there. And the brakes are always cool. Yeah, look at that dirt. That thing hit hard. The code has a thing where once it goes over, I think it's like 75 degrees, it'll go ahead and shut the motors off. But if it's coming in, at 70 degrees straight into the dirt, it's going to chop dirt, until it flips all the way over, or you throttle cut it. And what you're seeing here is just me being a bad pilot. I wasn't even doing anything automation. I was just flying it hard and got too close to the ground. But look how that fracture is. I mean, you can just pop it. I mean, it's like where you can barely see. See, look at that. Once it's joined, you can barely even see the crack points, even though it's entirely cracked. So the first thing I'm doing, I got that soldering iron on about 300, and I'm just I call it a tack weld, just like you on a vehicle. You do on a vehicle. You tack weld it in place, and I got this really cool thing. It's a little, you don't see the whole thing. It's a little handheld blower. It's actually an electronic battery. You charge it with a USB cable, but it's basically a replacement for a compressed air can. And so I can use that to rapidly cool this back down. Now what you see me doing now that it's tacked in place, it's right where I want it. What I'm doing is using the side of the tip to put a groove. And this is just like in industry, we weld two pieces of pipe together. You create a bevel on each piece that you're joining, and then it creates this nice V groove that you then take your filler rod and fill it in. I'm doing the exact same thing here. So I just created a groove on both sides of that centerpiece there. And now, very much like TIG rod, I'm just putting that hot iron there up against the rod, so to speak. And that's just a piece of scrap PLA, actually, that I'm using. And I've not really had any problem having dissimilar filaments. Now, ideally, you could just cut you off a few inches of the exact same filament, and that's going to give you probably the best results. But I had that little sample laying around, and I said, hey, I'm going to use that. And I like having different colors, because over time it's kind of like that Japanese art where they mend pottery. And Kylo Ren, his mask in the third newer Star Wars, which always raises my blood pressure when I think about those, but the like Kylo Ren's mask where you have a different color showing where it was mended. Now, you might be thinking, well, why not just use super glue? Well, one, glue you have to allow cure for 24 hours. Two, it just doesn't ever really work that good for me when it comes to strength applications. Yeah, I've tried about every glue known to man, and there's different ones I'm happy with to hold things together, particularly if it's just some type of, like a desk ornament kind of piece. But when I'm wanting to fly something and achieve flight with something, I'm not going to use glue. Maybe on the cover I might do that, but generally I'm going to weld it together. And really from here on out, after this project and me experimenting with this welding techniques for plastics, I'm going to design for tack welds over clip together. Because unless it's for removable things, like little hatches or whatever, but when I just make something because it's too awkward to print as one big print where you're going to want to snap it together, I'm actually going to design in pads that are intended to be tacked. And just, like a little hole will be there waiting for that plug weld to keep it together, because it's immediate. That's the thing. You hit it with the iron, it fuses together. It's not burning together, it's just melting together and becoming one. And you cool it off and you're going. There is no waiting overnight for something to cure or holding it for 30 seconds and clamping and all that kind of stuff. This approach here, it's just simply immediate. As soon as it cools down, you're ready to go. And it's amazing how much heat's in there. How like if you fry fish, how the heat just stays with it. The heat stays in there for a while. So if you go too quickly from one side to the other side might not be solid yet. It might still be flowing a little, so to speak, where once you start working the other side of the part, it could start drooping. And so all the time I'm looking at it and I'm adjusting, I'm moving it up. And when you see me grab that air and put it on there, I'm holding it in the position I'm wanting it to go solid into. Another thing I found, when you 3D print these, sometimes like if your printer allowed the part to lift off the bed and now the drone arm's bent,
The reason I have that ceramic there is because I can lay the drone arm face down and it'll be like a banana. On my older printer, it was bad about that. I lay it face down and it'd be a little bit like a banana, and I just take a hot air gun, one like you use to use on paint or heat shrink and different things, and heat the entire part up, and it will droop down to the flat surface. And then you just cool it, blow cold air, just let it room temperature cool, and you will have a perfectly flat part then. And so that was a great way to recover from my old printer that was really bad about delaminating off the bed as it printed. And then here I am, I believe I'm about to make that groove again. There I am doing my little cleaning my tip. Don't want to have so much on there it starts smoldering and sets the smoke alarm off, but somehow I made it through all this without setting that off. It's not too far above that bench. Now, in the links on this video and the original instructable this is for, you can see all the gear I have. There's a link there. You can see all the gear I have, and you can see all the parts that are involved on this. The instructable has all the 3D files, so you can print out all your own 3D parts and everything. And this one, it really is the epitome, or just the best project of all the projects. We made an R2D2 years ago now. Connor and I did. And that one really got us into the maker hobby. And we've done some really neat things with Wi-Fi, and, just making things talk and different things like that. But this project does it all. It does, Wi-Fi. It has introduces a web user interface that you can use your phone on. It does motor control. It does LED control. It plays music, like the little piezo button, that little round button there you see in the center of the flight controller, off to the side of the flight controller. It plays Danger Zone on startup. It's just every little trick to making with today's protocols. It uses SPI, it uses I2C, it uses Serial, it uses USB. It has every type of wire situation you would do in trace situation with where your I2C, you want no islands with your ground plane, and you want to have ground on either side of the traces and things, but then you have differential pairs where you want no ground plane between the two lines, and they got to be the same length and achieve a certain amount of impedance from point A to point B to work correctly. It's all amazing stuff, and every bit of that is in this small little project. And of course, this could be scaled up to a major project as well. I remember years ago when I first got into this stuff, over 10 years ago, my son had Connor, he had a friend whose dad worked in the, what's it called, NCIS or whatever. And I remember telling him, it's like, man, I can just mail order and make a drone, probably do all kinds of destruction. And his response was, yeah, but you probably couldn't weaponize it. And all I could think in my head was, try me. And of course, I never would. But then, of course, right now we're in the middle of a war, and drone tech is really flexing out there right now, because you can just program it to go fly wherever you want and serpentine all the way there, So here they are. They're back together. I got two of these at my 10-inch there. And that's pretty much it for getting these things together. So I hope you learned something. And if you didn't, definitely go to the instructable we have. That will be a great help to getting into this hobby. Take care.